Hey, this is Mr. Worden. Hope you guys are doing well. Everybody's healthy and chilling out. Today we're covering some odds and ends, and then you guys are taking a practice test and basically getting some work checked off, making sure everything's good to go. So getting started, we're gonna look at how Newton's laws correlate to pretty much everything, but definitely including tectonic plates. So we're gonna go back and review some of those concepts and talk about the continents and oceanic plates in particular. We're also going to talk about how radioactive dating works, which is a way to figure out how old something is. And then last up, we're going to look at relative dating also, so other ways to figure out how old something is too. So here are our vocab words, I think, for the most part. We're pretty much done with this unit, as you guys figured out from the fact that we're doing a practice test later today. I'll try to figure out a better way to get some Jeopardy going on Friday, and then our test will be early next week sometime. Let me know in office hours if you have any questions about any of these vocab words. Be on from 2 to 3 o'clock today. All right, so let's quickly review Newton's laws. First law says that if there's no net force on it, that whatever it was doing, it's going to keep doing that. If it was at rest, it's going to stay at rest. If it was in motion, it's going to stay in motion at that constant speed. So anytime you can tell that the speed of it's not changing, you know that if there are any forces on it, they're all balanced out. Everything's in equilibrium, they're all canceled. A zero net force is when an object just keeps on doing whatever it was doing. And then the contrast to that is if there is a net force, that causes acceleration, somehow proportionally to mass. So you guys know the second law, F equals ma, that's when speed is changing. Or it could also be turning a corner, direction could be changing as well. And then last up, you guys know that if one thing pushes off another, that other thing pushes back with the equal and opposite force. And back when we were working on this, we're using those boxes to make a free body diagram. We'd put arrows on, vectors, to represent different individual forces before we'd figure out how they all added up. So let's check out this box right here. This could be whatever you want it to be, but today it's a tectonic plate. First of all, what arrow do we typically start with? We typically start with a down arrow to represent the force due to gravity, the weight of it. And in this case, it's probably like a bazillion tons, since I'm imagining a continent is pretty heavy. I don't remember the exact numbers, who cares? Okay, we also know that the tectonic plates are moving along at a relatively constant velocity. They are not changing speed. They're just cruising along. So which of the Newton's laws is applicable here? The first one, when there's just a constant velocity motion, we know that the net force adds up to zero. So if I have a giant gravity vector down, what else do I need on this thing? I need some kind of an upward force. You could call this a normal force, like we often do, but I don't think of the mantle as like a firm floor because it's kind of plastic. So I think of this as buoyancy, a buoyant force. So basically the same thing that would get a boat to float. Buoyancy is providing the same upward force as the continental or oceanic plate's weight. It's downward force due to gravity. In addition, there may be some forces to the right or left on this, mainly because of slab pull. That is the thing that's helping these things cruise along at a constant speed. There's also going to be drag forces and friction opposing that motion so that the speed stays the same. However much to the right the slab pull is causing, trying to cause it to accelerate, we're going to have drag and friction slowing it down to the left with the exact same amount. So we're going to keep those two things in balance there. Again, we think that the continental plates are generally keeping the same speed. Over like millions and millions and hundreds of millions of years, they can change speed a little bit depending on what's going on. Like it hasn't been exactly the same for all of Earth's history, but for like within the time frames that we care about, they're effectively constant velocity objects. So again, any forces in one direction are going to be balanced out by some other force in the opposite direction, resulting in that constant velocity pattern. That's a big idea here. So whatever its weight is, you can assume the buoyancy is the same. Whatever force slab pull is causing it to get pushed to the right with, you can assume friction and drag are the same to the left. Everything's canceling out. That's an important idea here. All right, moving along. Radioactive decay. So first up, we're looking at some giant atoms whose size of the nucleus makes them unstable. We know that there's forces holding them together, which is the strong nuclear force, Very strong but short-range force. We also know that electromagnetism is a force that's trying to push them apart because a whole bunch of protons all have positive charge and like charges repel. So if at any point the electromagnetic force beats out the strong nuclear force, then atoms fall apart, they go through radioactive decay, and they'll change their identity into a different element. So one example that you guys have probably heard about from biology is carbon-14. Carbon-14 can change into nitrogen-14. And it'll do so at a really even, steady rate as far as probability and law of large numbers is concerned. We're not talking about one atom, we're talking about a bazillion atoms, like 10 to the 23rd type number of atoms. And the rate at which they fall apart gives you an indication of how unstable they are. Really unstable stuff tends to fall apart quickly, so the time that we measure for half of it to fall apart, called half-life, could be really short for those. Other atoms might only be slightly unstable and very rarely fall apart, and that would give these atoms a much longer half-life. Longer half-lives go with more stability, shorter half-lives go with less stability. And so you can kind of tell how stable something is from that. Now, one example that we're going to talk about is uranium-235 turning into lead-207 as a whole bunch of pieces fly off and do other stuff. By the way, those other pieces aren't gone, we're just no longer paying attention to them. Now, the half-life for that is 710 million years. So if I had like 10 grams of this stuff and I waited 710 million years, I'd be down to 5 grams. And if I waited another 710 million years, I'd be down to 2.5 grams. And if I waited another 710 million years, I'd be down to 1.25 grams. So you can see that every so often being the half-life, however long that is, half of the atoms involved decay. And that's why you get this curve chart here on the right, where every so often this represents the half-life, however long that is. In this case, we're counting by 710 million years at a time. Half of it goes away. And then another 710 million years. Another half of that goes away, bringing us down to a quarter of the original. And another 710 million years, we'd be down to 1/8. And then we'd be down to 1/16. And hopefully you're seeing the pattern. Now, of these original radioactive atoms, are half of them disappearing? No. They're changing into something else. So in this case, the uranium is changing into lead, in the example that we care about right now. So the lead atoms are popping up as the uranium atoms are, disappearing. They're switching over. Disappearing is exactly the wrong word. Sorry, I said that. So here's a question. How much lead did we start with? Oh, none. After 710 million years, how many grams of lead do we have? Well, in my previous example, if we're talking about 10 grams total, we went down to 5 grams of uranium, which means we'd actually go up to 5 grams of lead. And down here, if I'm at 2.5 grams of uranium, how many grams of lead do I have? 7.5. And then, if I go on to infinity time, and all of the uranium has decayed, how many grams of uranium do I have? 0 grams. How many grams of lead do I have? 10 grams. So basically, as the mass involved in one element goes down, the mass involved in another element is going up. And you can look at the ratio of those things to get even more information than looking at just one individually. Now, you might be asking, why are we talking uranium and lead specifically? Well, during igneous rock formation, that is like the lava or the magma is cooling off and getting solid again, depending on how fast it does that, it'll form zirconium crystals of different sizes. And you guys have probably seen some cool rock where it's got crystal facets in it. Little shinier, small zones, you can tell it's kind of crystallized. Well, zirconium crystals, as they form, they exclude lead. So within a crystal, right after it's formed, there won't be any lead atoms. They actually do a really good job of excluding it and pushing it outside the crystal layers. What they do have in them, though, is uranium-235 in very small amounts. And so when you have a brand new zirconium crystal, you can just about guarantee that it might have some uranium in it, but it definitely doesn't have any lead in it. And so what we can do is we can track as the uranium goes down and as lead does start to show up in the crystal, you can actually figure out how old that zirconium crystal is from the point at which it went liquid over to a solid crystalline structure. So you can use these to date how old rocks are. And the oldest known rocks on the Earth are about 3.6 billion years old that we know about, at least as far as ones that have stayed in the crust and stayed in solid form. Obviously, we think the Earth is a little bit older than that. We know that it's about 4.6 billion years old, but we don't have any rock that's that old. It's probably been recycled, destroyed, etc. So 3.6 billion years old is the oldest known section of the Earth's crust as far as I know. All right. You guys won't be doing any super advanced math on this, but I do expect you guys to be able to read a graph. If I told you guys that about a third of the original uranium was left, I would need you to go right over here to a third is left and find this spot and tell me that, oh, that looks like about 1 2/3 half-lives. See, I'm like 2/3 of the way over in this box to get to that spot. So if I'm at 1 2/3 half-life, and a half-life is 710 million years, I'd want you guys to multiply those and go, oh, okay, this is a little over 1 billion years old. So just be able to extrapolate out on a graph or interpolate, be able to find a spot and compare ages and the amount of material that's either left, or if it's the daughter atom, the one that's being formed, how much has appeared in that time. That's the main thing I want you guys to be able to do here. All right, moving on. Relative dating. There's other ways to tell how old rocks are, especially compared to each other. Real quick question. We got seafloor striping. This is where new rock forms with any magnetizable material, like any iron in there, in an arrangement that matches Earth's polarity at that time. So you guys know right now we got north and south. Definitely wasn't always that way. The Earth's magnetic field flips at fairly random intervals. So here's my question. See section 3 right here? I guess 3 million years ago or whatever. Where on the other side of the ocean floor do we also know that the rock is the same age? And you're like, oh, right here. Hopefully you can see that because it's matching stripe. This stripe was created at the mid-oceanic ridge at the same time that stripe was created at the mid-oceanic ridge. What's in the middle of the ocean is the youngest. Because this is a divergent boundary, the two oceanic plates are spreading away from each other, and we're going to get the youngest rock in the middle and the oldest rock at the edges. That'll be right before it gets subducted under the continental plates and melted back apart. Anyway, this striping pattern will be symmetrical on both sides, at least with respect to age. And you can say, oh, definitely that anything right here is going to be the same age as anything right over here. So we're going to have matching age ranges there. You can also check fossils that have deposited on top of that. And then you'll be able to see a fossil match here and a fossil match here. You'll be able to track this, not just like, let's say this is Atlantic Ocean. You're going to see that same striping pattern on the Pacific Ocean or the Indian Ocean or whatever else. So that's about it. One other thing we can do is we can look at geographic features. I want you guys to pop over and watch this Khan Academy video. It's just a quick recap of Pangaea, which is one of the supercontinents. It's the most recent one that we know about. And you can see how things fit together. You can do a climate analysis. You can even look at the shape of the coastlines and stuff like that. All right, that is it for stuff that we need to finish up with. You guys are good to go on all of the earth science stuff now, assuming you've been keeping up with things. Again, I'm happy to answer questions in office hours. I don't see too many of you guys. I'd love to see more of you pop in and just get questions answered or say hi. Last up, if you are bored at home, I have a challenge for you. Since we're learning all about tectonics, you should learn to tectonic dance. Watch some YouTube videos, try it out. Good stuff. Kind of same era as shuffle, hardstyle and jump step. It's a pretty good workout if you want to try it. And yeah, maybe we'll have a dance off or something. All right, that's about it. Yeah, see you guys in office hours. Let me know if you need anything. Bye.